Hello students, welcome back. Previously, we went through the definition of the vectors and their standard features, magnitude, direction, and algebra. What do you mean by vector algebra? We are talking about addition and scalar multiplication. And then we went through some examples. Yes, this is the most important example of a vector, the position vector. So whenever you have a point, you have a position vector. Suppose that you are sitting at the origin and observing any point. Any point will give you a position vector and vice versa. So there's no difference between a point and a vector. So the parenthesis expression for a point versus triangular bracket expression for vectors, there should be no distinction between one and the other. Remember that. Now we went through magnitude as well. And the magnitude formula is here, and it's easy to deduce. It's Pythagorean. Square root of x squared plus y squared, the square root of horizontal squared plus vertical squared, because you have a right triangle here. You can form similar kind of triangle method here for displacement, but as I said before, that's comparatively less important. And finally, I think we discussed vector addition and scalar multiplication in terms of coordinates. We can just add up the coordinates, x coordinate and y coordinate separately. If you have z coordinate as well, do the same. And scalar multiplication is equally as easy. Just multiply k to each component. A visualization, yeah, okay. Here's a justification. Please note that this blue right triangle and this blue right triangle are congruent, and same for this red and that red. And as for the x coordinate, x1 here for blue and x2 here for red, and that's going to give me the x coordinate for this purple. As for the y coordinate, y1 for this blue and y2 for this red, and add up, then that's the y coordinate for this purple. So that's the justification. x1 plus x2, comma, y1 plus y2. And then the justification for this, that one's even easier. It's just a similar triangle. This right triangle and a little bit bigger right triangle here, multiplied by k. So that same k applies to all sides, horizontal and also vertical. So that we have kx and also ky. So those are the justifications, and then we can do vector addition and scalar multiplication through components like those. Let's see, do we have time to do some examples associated with that? I guess so. Oh, we need some more preparation. Sorry about that. This will have to wait. Sorry, just a little bit more. Let's discuss the concept of unit vector. What is a unit vector? It's a vector with magnitude 1. How do I get that? Start from any vector and then multiply by 1 over its length. Now, if you take this length, you're going to get a certain length, whatever it is, and then divide by the same length. What do you get? You have to get 1. By the way, we went through that kind of expression over here. You see, what do you mean by, oops, sorry about that. What do you mean by this v1 hat and v2 hat are the same? v1 hat, this is a unit vector in the direction of this v1, and v2 hat, that's a unit vector in this direction. Say, for example, if this blue vector has length 4, okay, divide by 4, so up to here. So you're going to get a unit vector. Same direction, but length is 1. The red vector has a magnitude 2, divide by 2, then you have smaller vector here. That's a unit vector, same direction, but the length is 1. And if you do that, these two are the same. And that's the very expression associated here. We use this hat notation for unit vectors. There can be many unit vectors, but the most important types of unit vectors are these. INJ, 1, 0, horizontal, and 0, 1 vertical. Here's a visualization. So 1, 0, this horizontal, that's visualized in blue here in this picture. And then J is 0, 1, that's red, vertical. You can use standard arrow notation, or you can use this hat notation because these are unit vectors after all. But this expression is rather rare. You either use ij like this with arrows, or do not use arrows at all. Here in this example, 3, 2, so 3 times blue, so I go 3 units to the right, and then 2j, 2 units up. So component expression, a, b, versus the ij expression, ai plus bj, they're the same. Did I say ai, bj? Here I wrote xi plus yj, so I should have selected better character here. Here x value is 3, y component is 2 here, x coordinate is 3, y coordinate is 2, 3, 2. I hope you can see all those. Okay, now we are ready. A is given like this, and B is given like that. And B, this one is straightforward, 4, -3. But A, well, this is an ij expression. So how can I rewrite it into the triangular bracket expression as component? We can rewrite it as 1, 2. Is that clear? 1, 2. This one here, as I highlighted in blue, is 1, 2. And this one here, which I just highlighted in green, that's the same as 4i minus 3j. Well, actually, let me do it here and there, and then not here. So, which expression shall I use? Component expression or ij expression? Well, let's do both. V is 2a minus 3b. Okay. And then that is 2 times 1, 2. Minus 3 times 4, -3. And then I'm applying this scalar multiplication by 2, so multiply 2. 2, 4. There you go. And then I can multiply by 3, but I decided to multiply by -3 directly. So -12 and then +9. That came from green, so let me highlight that part in green. Okay, and then let's add them up. By the way, here from second line to third line, I just used this, multiply by k. Now I'm about to use this, adding up. 2 minus 12, that's negative 10. 4 plus 9, that's 13. And that's the final answer. Is that clear to you? Let's see, what did I do here? Yes, the very same computation. Scalar multiplication, multiply by 2, multiply by negative 3, and then add them up, component by component. You can use this, or you can use IJ expression and then use the usual algebraic manipulation. Break up the parentheses and take the like terms. 2i minus 12i, so negative 10i. 4j plus 9j, so positive 13j. Either way, you get the same answer. Which form do you prefer? Me, I usually use component expression, but there are people who prefer IJ expression. A lot of physics textbooks are written in IJ form. All right, let's go to part B. Let's find the magnitude. Oh, that's easy. So, magnitude of V. Square root of, what's the x-coordinate? And what's the y-coordinate? Remember that? I already forgot. Let's go back to the answer. X-coordinate is negative 10, so this is negative 10 squared. Y-coordinate is 13, so this is 13 squared. Okay, just Pythagorean. Horizontal squared plus vertical squared, and then square root. And that is 100 plus 169. So square root of 269. Okay, there you go. That is the magnitude. By the way, our textbook authors this expression of magnitude is this absolute value notation, but a lot of people use this expression, use double vertical bar. I prefer the latter notation a little bit more. The reason? This way I can clearly see the distinction between the magnitude of vector versus the absolute value of a scalar. So if you have just single vertical bar, then that's just the absolute value of a scalar. And then if you have double vertical bar, then that's a magnitude of a vector. Our textbook author, on the other hand, does not bother with this second expression here and does this one only. That's fine too, but as a matter of fact, there are more mathematicians that does this way than the other way actually. This one is majority, and I like the latter one as well. Anyway, this is our textbook author's expression. Okay, that was a magnitude. Finally, the unit vector. Unit vector, well, unit vector expression is this hat notation. Hat notation. And then that is 1 over magnitude times this vector. So this is scalar, so same direction as the original V. But if you take the magnitude, this one has magnitude of square root of 269 and divide by square root of 269. So overall, I'm going to get 1. Like this. This is a unit vector of the direction of V. What did I do here? Yeah, the same thing. Either I use this or IJ expression. Either way, it's the same thing. That completes section 1.